All right, so this problem is to use logarithmic differentiation to find the derivative of this function here. You could just take the derivative using, well, this is a quotient, so you could use the quotient rule. And then within the quotient rule, you're going to need the derivative of the top, which is the product rule. And even within that, you've got power rules and chain rules, and you can do it. It's pretty straightforward. It's just kind of long. So instead, we use logarithmic differentiation. And the idea with logarithmic differentiation is you take the log of both sides first, and then you take the derivative implicitly, and then solve for dy dx. So here we go. So I take the log of both sides. And the reason is I do that is because this is all products and quotients and powers, and those break up nicely. I'm going to use three properties of the log. The log of a times b is the natural log of a plus the natural log of b. I'm going to use that the natural log of a divided by b is the natural log of a minus the natural log of b, and likewise the natural log of a to the n is n times the natural log of a. Each one of these things is a property of exponents that's just turned around. This one is saying, what's the exponent that you need for a product of two things? Well, it's the sum of the two exponents. What's the exponent you need for a quotient? Well, it's the difference of the exponents. And what's the exponent you need when you're raising something to a power to another power? Well, it's the one power times the other power. Anyway, so what we have here is the log of a quotient, right? We're going to split that up. We got the natural log of y still over here. So this would be the natural log of the top, x cubed times x minus 9 squared, minus the log of the bottom, x squared plus 9 to the 5th power. Okay. Now I want to take this log of a product and split it up into the log of a sum using that up there. So I've got the natural log of y is the natural log of x cubed plus the natural log of x minus 9 squared. And I still have this, not equals, I still have this minus natural log of x squared plus 9 to the 5th power. So I've taken care of the quotient, I've taken care of the product. Now I've got all these exponents that I'm going to pull out. So the natural log of x cubed is 3 times the natural log of x. The natural log of this thing squared is 2 times the natural log of this thing. And likewise, the natural log of this thing squared is not squared, but raised to the 5th power is 5 times the natural log of that x squared plus 9. So this is still the natural log of y. Be careful at this stage. What I see sometimes people do is they then try to break this up, where the natural log of x squared plus 9, or they try to pull this 2 out. The thing is, this is the natural log of a sum. And I don't have anything that tells me what to do with the sum. I have something to do with a product and a quotient and raising to a power, but not a sum. So this doesn't break up anymore. This doesn't break up anymore. This 2 doesn't come out because it's not the whole thing squared, it's just a piece of it squared. This is about as far as I'm going to go. After you do a couple of these, I go straight from this step to this step. I skip all this stuff in the middle because I know this, it's going to just be a natural log of y on this side. But I also know that all the stuff in the numerator, all the factors in the numerator, are going to end up with their own terms here being added together, and that the coefficient out in front is whatever the exponent is, right? So this x cubed is this 3 natural log x. This x minus 9 squared is a 2 natural log x minus 9. Stuff in the denominator is essentially, this is like a negative 5 exponent because it's down in the denominator. So I have this negative 5 times the natural log of the x squared plus 9. So you get so that you can see all the factors in the numerator are going to be terms with plus signs in front of them. All the factors in the denominator are going to be terms down here with minus signs in front of them. And the coefficients are just the exponents. Anyway, so Sometimes it seems like a long process, but the process is the same, and you can skip a lot of steps and just get from here to there. Now I'm ready to differentiate. I'm going to implicitly differentiate. So I'm going to take the derivative of ln with respect to x, and that should be equal to the derivative with respect to x of all of this stuff. Right? 3 ln x plus 2 ln x minus 9 minus 5 ln of x squared plus 9. Okay. The thing is, taking the derivative of the natural log of something is really nice. It's just 1 over that something times the derivative of that something, right? So 1 over y times the derivative of y. The derivative of 3, well, the 3 comes along for the ride, times the natural log of x, well, that's just 1 over x times the derivative of x. The derivative of x is 1, so we generally don't write it down. Plus 2 over x minus 9 times the derivative of x minus 9. But that's 1. Minus 5 times, I want to do a 1 over x squared plus 9, but then the chain rule says times the derivative of that x squared plus 9. So this numerator becomes a 2x. Now solve for dy dx. That is, multiply both sides by y. I've got 3 over x plus 2 over x minus 9 minus 10x over x squared plus 9. And if this were an implicit problem, I'd be done perhaps right now. But this didn't start implicitly, this started explicitly. And I actually know what y is as a function of x, right? It's my original, where is it? It's my original function here. So that's what I'm going to plug back in for y. And I end up with dy dx equals x cubed times x minus 9 squared over x squared plus 9 to the 5th power, that's the y, times all this stuff. 3 over x plus 2 over x minus 9 minus 10x over x squared plus 9. Okay. Now we have the derivative of y as a function of x. It's possible that you could multiply this in and some things will cancel out, but I'd be inclined at this stage to just leave it like that. If there's still some things unclear about this, please ask, and we'll do our best to continue answering.